the funding only in 2 weeks, and so then we'll hopefully also get some. Yeah, next thing I want to mention is we want to spread the word about this event, because it's a really nice event, so I hope and I'm quite sure that you will be very happy about what we prepared there, and therefore please share, make photos and so on. So as you've seen already, we have the Facebook page, then we have the LinkedIn page, then we have Twitter, and on all three we'll also post some articles that come from our blog. We have the YouTube channel, so there you will find all the recordings from the sessions that we are doing today. And as I send you in the email, we'll also do live streaming. So if you have friends at home who want to join online via YouTube, tell them, send them the link. So the link is futureiot.org/stream. And yeah, we have the blog. And if you are a writer and want to write an article for the blog, you are more than welcome to. AI here as an additional incentive for posting. Okay, then I thought about something. When we do some tech meetings here, I always want to have something that has to do with art. And we have the city tours, so this is already very nice. We have the beer garden visit and so on. Okay, great cultural program. But I also thought, let's create something together during this event. And for that, you see the 3 walls here. I also brought some printers where we'll print out photos if you send them to us. And the idea is that whenever you feel like, okay, you want to be creative now or you want to relax a bit, go to the wall, take a pen, take some of the photos, glue them there, and write something. And so the idea is that we create an artifact that we have then in the end. And yeah, so my hope is that this will be quite fun and we'll have something really cool at the end. Okay. So this is clear. So everybody is welcome to contribute there. But the good thing with art is that nothing can be wrong. It's not like code. Okay, good. Then, as said already, share your pictures. So you know this link already, and so the microphone is. Oh yeah, now it's better. Okay. So you know the link already. So after my talks, I will also change the page that you see there. At the moment, you still see the PhD posters. Still, if you make photos, please upload them to this website. It's also very well working with the smartphone. I tried this out, and we will then print these out and maybe use them on Twitter and so on. So it would be great if you could share some of the impressions. And the link is also on the walls here, where you also find the QR codes for the social media here on the sides. And yeah, okay, good. Then, as said, we have the Twitter wall. So if you Twitter something with the hashtag IoT AI, then it will appear directly on the wall. And so this is also interesting, and people will probably also have a look during the talk. And Fabian was also promising that some important people from Siemens will Twitter for us, and so we're looking forward to it. The tweet will then be in golden on the wall. Okay, good. So this is the Twitter wall, and yeah, then another thing that we brought, I just started. So this is what you will see on the screen in the back, where I currently see the preview of my talk. So this is a game, and the team that does Challenge 3 will do something with this game, so they will create an even cooler game. And so, yeah, here you see how people are playing with it, and so this is about laying your hands on these 2 poles here, and then they will give you a light signal, but it's not synchronized, and then you have to remove your hand as fast as possible, and the one who's faster wins, and it's actually quite fun, and the Challenge 3 team will implement something even cooler for that. Okay, so if you're bored in between or you need some relaxation, you can just go there, play a little bit, do something with the wall, walk upstairs, downstairs. Okay, good. Then the next point is the agenda. So you know the agenda already is also hanging there. As additional point, we would like to make a group photo today after lunch. And so the idea is that we just do it here. We stand here and do the group photo here. If the weather is better tomorrow, we might do another outside. Okay, so this will happen after lunch. So try to keep clean during the eating, and then after the photo you can get dirty. Okay. Yeah, Tuesday. So, okay, well, let's say something to the agenda here. So, when we thought about how to put the program, we thought that today we do a day where we have lots of lectures and input for you, and end with presenting you the challenge, and then having the nice social event with the city tour and the beer garden place with the best beer here in Munich. And so today you get lots of lectures, lots of input stuff. And then the next days are more in the area of that you're also doing something with the hands-on, and therefore tomorrow we'll have 2 hands-ons for the machine learning here, and we'll have 2 lectures, and you also have quite some time for doing the preparation of your challenges. And in the evening we have the second tour. So this was also important for me, that we have 2 social events, so that you also get fed every day. So you will get food every day from Monday to Wednesday, so you will not starve. And the third day then you will have even more time for working on your challenge. And so there we again have 2 interruptions, with the keynote lecture in the morning and 1 in the afternoon. And besides that, on Wednesday the plan is that we work until as long as you want to work. We'll order some pizza probably, so that we can eat here, and this is then a true hackathon day. Okay, and then on Thursday we have something special, so Fabian will introduce it later. So on Thursday we have the pitch, and this is where you will present your project to a jury here, and the jury will then grade your presentation, and then we'll have a winning team, and the winning team will also get a special gift. And so this is the plan for Thursday, and so there I would expect that we end probably 4:35, around that. Okay, good. Lunch. Okay, so the lunch organization is as follows. So we'll go for lunch in groups. If I remember correctly, Katharina, Fabian, and I will each take a group, and you already did the pre-selection with Katharina before, and if you have any questions around that, just approach Katharina. You are invited for lunch on all the days. Everything that is in here with the drinks and the snacks and so on is also included, so feel free to consume as much as you want or can. Monday, Tuesday we'll take you for dinner, and Wednesday we'll have food here. So you will have food until the event ends, and so you will definitely have at least a take-home that is here, and hopefully also one that is here. Okay, good. Yeah, so this picture is from close to here, and so here you already see the Frauenkirche, and you see the Olympic Tower here, and so we'll visit the Frauenkirche. So here you see the Isar River. And so you will see beautiful parts of Munich. If you are staying for longer, the Olympic Park here is also interesting. So this is where you have this huge glass roof construction, which is I think the biggest, at least in Europe or even worldwide. So this is also a very nice place. And besides that, the city tours will not be forever. You can just walk the similar paths again. You will discover very nice places here in Munich. Okay, city tour Monday, so this is the plan. So there you will see cool stuff. We'll start with something very cool and end up in the Augustiner Beer Garden. As you know, we have the WhatsApp group. Those of you who are not in it yet, join it, because the idea is for the city tours that one of us is doing live share of the location, and if you lose us, then you can find us through the WhatsApp location tool. If you lose us and you don't have WhatsApp, then we'll meet later in the Augustiner Beer Garden. This is also a good place to catch up. If you think you could get lost, you can also get my phone number, then you can also call me. Okay, good. This is the city tour on Monday, and on Tuesday we'll have another city tour which goes to a slightly different direction. So this starts then at Marienplatz, so we'll also see the Marienplatz today, and then we'll go a little bit to the where do we go? To the west, and go to the place where you already see all the Oktoberfest tents, because everything is almost already set up. We'll walk over this area, and then we'll go to the beer garden there in the end. Okay, so this is the location. So we are currently in this area here. Behind, so there you see the challenge number 3. Here will be the challenges number 1 and 2. And upstairs we'll have the challenge number 4. And we'll also have a studio where we'll do some interviews with those people interested to do so. This will also be upstairs. We will take photos and also videos. So if you don't want to be prominent on the pictures, you don't have to, and if you don't want to be on the group photo, I also don't force anyone to do so, but it might still be that you're accidentally on the picture. And so is this okay with everybody? So before beer garden, yeah. In the beer garden, they will be only on the private share page. Okay, who has a problem with that? Okay, good. Then, yeah, we'll shoot some videos, as I told you. So one thing that Nicolas and I are doing is we are also creating a course on edX, which is the one of the e-learning platforms about IoT and AI. And for the trailer, it will be cool to get some input from some people here. So there you will have some questions like, okay, why do you think AI is important? Why do you think IoT is important? So this is what we'll do. Then what I would love to do is to create some more videos like the one that I created when we came here. And therefore it will be cool to have just some interview scenes where you say like, okay, this is where you come from, this is what you're most interested in, and stuff like that. We'll also walk around and make some videos of the challenges, so just that you know, okay, so this is what will happen with the videos. Yeah, for the trailer, we'll approach then the challenge desks and ask the people who's interested to join there. If you want to see how such a trailer looks like, you can go to this course. This is one MOOC that we also created on edX that you might have looked at because I sent the link around already. When you look in the trailer there, I also interviewed some people, and they also said, okay, why is the internet important, for instance? And this got quite cool, and I have something similar in mind. Therefore, I want to do these interviews. Okay, good. Yeah, then we live stream. So this is URL of the live stream, and probably it's currently working. So the people in the back are not acting like crazy. So I think it's working. And yeah, please tell all your friends. They can even ask questions over the chat. And then when we have the Q&A after the talks, then the people in the back will reflect the chat questions also to the room here. Okay, and as we are streaming, it's also important that when you have a question later, that you take one of these microphones. First of all, because the people in the room here can hear you better then, because the acoustics is not perfect. And second, that the people in the stream can hear you. Okay, good. So, yeah, I think I caught up a little bit with the time. Yeah, that's good. Do you have any questions at the moment regarding the setting, regarding the social events? So whenever you have something, approach us. So Fabian, Katharina, my team, and me, and also the others are always happy to support you and to help you. Because like all the other events that I'm co-organizing, the focus of the event is of course you. And so therefore we try to do everything so that it's most cozy and nice for you. And this is also why we spend so much time in this room, because it's very important to have a nice working environment, because this really fosters good work and creativity. Okay, good. Then this was the first talk. Yeah, then welcome and enjoy. And I will try to fix this mic for 1 minute, and then we will continue, because then Chris and I will do the first keynote. Okay, so yeah, let me just trying to fix this mic. Then probably you should stop the stream and we start a second stream, and you can put the funk. Yeah. Okay, so how did we structure the talk? We have 3 parts. Yeah, it was too fast. So first of all, I want to give you a start why it's important what we're doing. And it's not only important, but it's actually a totally new area of computing that we're currently entering. And I want to briefly motivate it and also show you a little bit about the history of computing, because this is something that everybody should know, and it's also leading us to our topic today. Then we look at IoT meets AI from the industry perspective. Chris will take over and will present us challenges and opportunities that are currently very important for industry, for Siemens in particular. And then I will give you some intro to research. What is the research? What is my team at the moment doing? Which are challenges that we're currently tackling? Okay, good. Starting with the first part. Are we in the matrix? Okay, so you probably have seen the movie. So who has not seen the movie? Okay, so one. Who has seen the movie? Okay, you all have hands. Very good. Okay, so yeah, so this is a screenshot from the movie. Normally I show a little video sequence, but I was not sure with the copyright if this is okay, therefore I just put the pictures. So these are these three agents, and when you think about the scene, this is one of the key scenes. Then soon after, he sees this, which is like the Matrix, even though he's currently in it. And what do we see here? Well, we see that we have something that symbolizes here the code that is running, and the code is creating our reality. And are we in the Matrix? So, well, I would say we are somehow in the Matrix today, because with the IoT, we are able to control our environments. So this is now a private space, for instance, or an office space like this one here, and we have sensors and actuators distributed, and these sensors and actuators are connected to a brain, which in the case of computer science is then a processor, and then we can control our ambience by the programs. And a Mqtt program, or something that is currently en vogue, is using machine learning. This is also something that we'll do in the upcoming days. And what I like to tell people when I say, okay, what is my research, what am I doing there? Well, I'm kind of doing magic, because how is doing magic? Magic is you say a spell and then something happens and something changes. And doing smart space orchestration, so by using software to control the environment, is something very similar, because it's like when you have your smartphone here and you start the app and then your environment is suddenly starting to transform. Or you don't even need that, you just enter the space, the lights go on and something like this is happening. And this is like magic. It's like putting a spell on the environment, and the spell is your programming language, and you can program the things that you want to orchestrate. And this is what we'll do in the upcoming days, and I really like this analogy, because I always wanted to be a wizard, and so somehow we can be a wizard. This one is also a very good example, the smartphone, because it's a small IoT space. It has also sensors and actuators, and they are inside this shell here, and you can use software to control them. So these are the key issues there. Okay, so yeah, we're somehow in the matrix. We cannot only control the private spaces, but also public spaces, industrial spaces. This is what we look at in the next days. When we look at a time frame here, so probably before many of us were born, we had the area where we had mainframes. So this was people going to the cellar and using the computers there. Then afterwards, in the 1980s, 1981, we had the personal computers. Huge change. So it was not something happening in the cellar, but it was you could take it home. You all grew up with personal computers. Then it continued. The next wave that we have was mobile computing, with the Apple devices as iconic devices, because they managed to, for the first time, to really implement this software for controlling the hardware, creating a software ecosystem for controlling the smartphones, for managing them. This was also a milestone because it was having multi-users using the same device. And what is happening today is that we have pervasive computing, and while mobile computing here means computing everywhere, so we have our smartphone with internet connectivity, we can use the backbone everywhere. Pervasive computing means that we have computing in everything, so we can remotely manage all the entities that we have in our spaces. These public displays are good examples for it, for applications that we might have in the near future, that you are in the train station and the display is reacting to you. For advertisement, you partly have it already. And the last two together, they are called ubiquitous computing. What is interesting here is the interaction scheme. So at the beginning, you had multiple people using one computer, personal computer, you had one person using one computer. Then we shifted towards one person using multiple devices. So I'm quite sure that all of you have at least two compute devices with you. And when the pervasive computing will be reality, or how it is already when you're in factories today, for instance, is, or in buildings that are smart, is that you have many people that are using many devices, and so the relationship is not anymore this is your device, but it's you and you're entering a space and there are devices and you're interacting with them. Okay. Good. So these are three phases, and the third one is the thing that is currently getting reality. And now let's have a closer look at how this path went. And so these are 5 pictures. So these are 5 videos that I want to share with you. And I want you to guess when the video was taken. The quality of the videos is just like that because I took them from the internet. So you cannot necessarily guess from the quality of the video when it was taken.
I'd like to see you while I'm working on it. So before I can do that, I have to set up my display in a certain way. So I see it over like that, but it leaves a corner up there, and I say, now computer, do the automatic switching that is bringing in the camera picture from the camera mounted on his console, such as the camera mounted on mine. There you go. That's great. Now we're connected audio, you can see my work, you can point at it, and I can see your face, and we can talk. So let's do some collaborating.
Okay, so we have seen there's some kind of video chat and some interaction between the 2 people there. Yeah, when do you guess was this recorded? 83. Earlier, later? Who's for earlier? Who's for later? Okay, so actually it was recorded in 1967, which is very amazing, because as I will show later, this is very similar to Skype for me, and the idea and the technology were there back in the 1960s, 70s. However, this was done using analog technology. So they used video mixers for doing that, but it's still amazing to see. And so this is called the mother of all demos. It's Douglas Engelbart. In this demo, they also presented the mouse. And if you want to see the real devices of this, you can go to Santa Clara, I guess is where the Computer History Museum is. There they have the original stuff standing. Okay, 67 they had that. Let's continue to the next guy, Alan Kay, by the way.
By trying different sizes of things, we realized it should be really thin, should be light. It would have a stylus for drawing on it, wireless network, flat screen display, keyboard, and all that stuff. So this is kind of the thing I used to hold up back then of what computers should be like.
Okay, so also amazing. So this is another piece of computer hardware. Any guesses when this was recorded? What did you say, 75? Okay, let's have a look. So it was a 72, almost, very good. So you're sensible now already? Okay, so Alan Kay is the guy who did lots of human-machine interface stuff. He did also the logo programming language, so he's also a very important person, also like Douglas Engelbart. All computer scientists should know that the two exist and what they roughly did. Okay, now we come to the third.
Here's what I've drawn for the animated section. It's an MPAD, a base station, and a workstation. See anything you want to add to that?
Well, we could add a second pad to show that there isn't a one-to-one correspondence between pads and base stations. I know. We could put it on a tether.
Yeah, I think that might work.
What are you guys working on?
It's the animation section of the MPAD video. Can you think of anything we might need to add to what we've got here?
Well, perhaps we can add a base station here and a radio. To show that the MPAD can roam between base stations. Definitely. Seamless, uninterrupted communication is an important issue. How's it going?
Oh, hi, Ron. Well, we've added an MPAD tethered to the first base station, and we've added a second base station to animate roaming. You see anything you might want to add?
Well, that looks pretty good, actually. But I know Bob had a few ideas. He's still busy hacking away for the demo, but we should be able to reach him. Bob, this is Ron. Are you around?
Hi, Ron. What's up?
Hey, we're working on the MPAD animation right now. It's all up on WB. Is there anything else you wanted to add to it?
Let me see. Let me take a look. How about adding a second pad out here, maybe at a remote location, and it could show off the audio features of the pad.
Okay, nice.
And so the amazing thing about this demo is that this is the real first time where they have all this technology implemented, and so they have wireless communication and so on. And this was actually not so much later. It was in 1998, even this video. And this is at Xerox, the US company that did the copy machines and managed to invent mice, Ethernet, and so on, but not to commercialize any of it. So if you read the book about Steve Jobs and Bill Gates and Xerox, there you can read how they did not manage to commercialize the inventions, and then Apple and Microsoft did. And for wireless, interestingly, they used infrared back then, and today you might know that with the LED lights, there's also something where they try to, or they do not try it, I mean they did it, communicate over the frequency of the LEDs, so it's interesting because it all comes back again. Okay, so now when we continue with the timeline, we see that in 2003 we had Skype, so it's very similar to what we had here, from the idea at least. Then in 2008 we had the iPhone here, which is similar to what LNK is doing there. And in 2010 we had the iPad as bigger device. And so today, what do we have today? Well, I brought also 2 videos for that. So what we have today is, first of all, this one here. Here we see autonomous driving, and what we will see now is how this car, there will be a car coming from the right, and the autopilot is automatically preventing an accident here. And so, yeah, so now the car will be coming. Okay, and so the autopilot was noticing that and was going over. This partly also uses artificial intelligence technology. So this is very nice that we are able to do such things today.
This is the automation system
this is
running in my house right now.
Second
and just
example.
give a quick explanation of what these things do and how they work. So we're going to go ahead and start in the first box here and get this guy opened up. Open all this guy. First thing we're going to do is we're going to turn the lights back on.
Okay, and so why did I show this video? Because it's not only big companies that are able to do things, but when you're at home and you have money and time, then you can build your own system. So there, the Arduino or the Raspberry Pi are products that were not available 15 years ago, and today you have 3D printing and so on. So we are living in a very good time for doing this magic in the environment, because we can create all the things. If we miss some tools, we can just print them and connect them. We only need some basic technical skills to do so. And this is a really great thing. And if you would have been sitting here 15 years ago, then people would have paid you very high amounts of money for creating something that you can do today as a toy project on the weekend, because you just didn't have the tools from the hardware side and also not from the software side. Okay, good. So this brings us back to the overview. So there are also some references if you're interested to continue reading in that direction. And yeah, so this was the introduction to why does it matter? IoT meets AI, where are we at the moment? What is the history where we come from? Okay, and that brings me to handing over to Chris. So, do you know this presenter? Because it's irritating, because it's just a guru, but you see the point there, and it's also on the recording. So I would recommend use that. If not, I also have another presenter.
Okay, so good morning, everybody. For the next, let's say 15-20 minutes, I would like to give you some insight into IoT meets AI from an industrial perspective, certainly not covering every detail and every aspect of this topic, but more setting the stage for the presentations to come and also for the challenges that you see on the program. So my name is Chris Winkler, and I was already introduced by Fabian, so thank you for that. And that's why I can directly dive into the topic. So when I think about industrial IoT, our vision of the industrial IoT finally is the collaborative industrial IoT. That means that we will see a world of smart things that collaborate in a self-organized way to accomplish tasks, complex tasks, in a goal-oriented manner. So you are not tasking the things as we did in industrial automation for the past 20 years, where much of the automation was pre-programmed and pre-arranged, but the things are able to detect what they should do and who could help them, with whom they can collaborate to do things. And to achieve this, of course, we have a mission. That means we need to make the things smart. So from an industrial perspective, how does the evolution of the industrial IoT look like? So as you know, the whole thing started, like shown here on the left side, with more this cloud-centric idea of IoT, which is also, I think, quite predominant in consumer IoT settings, where machines and also sensors send some data to the cloud, and then you find some applications on the cloud that do magic things with this data. Easy things like dashboarding, but also predictive maintenance and all those nice applications. But industries very fastly realized that this cloud-centric, this cloud-only model doesn't really work for all the industrial requirements. And that's why we now are in a phase where we push more and more of the processing capabilities back again down closer to the field, either to edges, edge devices, dedicated compute resources that can host edge applications, or even to the devices themselves, making the devices smart. And why is this so? Well, one reason is because of the sheer amount of data that you need to process for industrial IoT applications. Think about vibration data, think about imaging data that would be that you would need to transport the cloud to the cloud for analysis. So that this is on the one side a bandwidth problem, but also a cost issue. A next argument is that is reliability. So if a cloud connectivity is part of your process, and your process somehow needs to work reliably, then it is probably a good idea to have this part of the processing locally closer to the field, instead of having this unreliable cloud connectivity within your control loop. The same is true for real time. So if you need to act in real time on the data that you want to process, then having some cloud sitting somewhere, maybe even in a different country, might be a bad idea. And last but not least, an argument that we often hear is data privacy or intellectual property protection. So many companies are reluctant to send all of their data via public networks to a public cloud, even if you can convince them that everything is somehow encrypted. But nevertheless, as soon as you do processing in the cloud, the encryption is broken. And that's why they are not so willing to send all their data to the cloud. Now, this is the phase that we are currently in, to introduce more and more capabilities closer to the field, on the field devices, on the edge devices, and this can be data pre-processing, but also can be machine learning or trained models and all that stuff. So to say, a logical next step of this evolution is to come to this collaborative IoT, where the smart machines start to interact with each other and start to perform tasks along given goals autonomously. Autonomous cars, as we've seen them on the video, is certainly one example, but we will see increasingly autonomous machines also in industries. But if we now talk about smart things, what is the smart part of the smart things? And we tend to use these three terms here to describe what the smart thing is for us. It's the first thing a smart thing needs to do is to somehow create a self and situational awareness. So get an idea about the own situation, the own status, but also an idea about the environment, what is in there, which other participants are in this environment, what can they do for me. So this is creating this self and situational awareness. The second step is certainly to be able to integrate into this environment and to adapt to this environment. And last but not least, and that's what the ultimate goal is overall, is that the smart things then autonomously can perform tasks and collaborate in this setting. Now, what is the prerequisite for this smartness? The prerequisite, the self and situational awareness, is something that also we as humans, of course, use when we want to integrate into an environment and then start doing things in this environment. Oh, This is maybe not the latest presentation. Okay, so I start with this one here. And how humans do it is more or less depicted on this slide here. So we have, as humans, we have a lot of sensors. Our eyes, our nose, we have touch sensors, vibration sensors, whatever you think. We do, or our brain does a lot of pre-processing of the sensor values, and nevertheless, to really make some meaning out of this raw sensor data, you would also need some background information, so some experience, some knowledge. Like on this example here, you may somehow be able, or your sensing may be able to generate this picture of obviously a church or cathedral, but only combined with background knowledge, with background information, you are now able, or you can know how to behave in this environment. For example, that this is an environment where you typically should behave a little bit silently, or where special rituals are typical. So it is the combination between sensing, data processing, using different types of processing. In the case of humans, of course, some pre-programmed, some learning, and then knowledge and experience. And the same is, of course, also true for technical perception. So making sense out of your environment involves sensing on the one side, pre-processing the raw sensor data to come to, let's say, meaningful information from the sensor data, like, for example, doing a Fourier transformation to calculate frequencies. But to really make sense out of the data, also here the combination with background knowledge is really worthwhile. We call this often digital twin of the system under observation, and the digital twin could contain numerical models, physical models, also learned models, trained models, but also information about the system environment. For example, if you measure a vibration value on the left side and you calculate frequencies of this vibration, it might be interesting that you know that this is a vibration, but the value of this information increases a lot if you know that this measurement is taken on a bearing, and this bearing belongs to an axis, and this axis is part of a windmill, like on this picture here, and the windmill has 3 blades. So a typical vibration scenario for a windmill with 3 blades would look like this and this. And if you observe an abnormal behavior or normal pattern of your vibration, then you can also take the wind measurements into consideration and deduce that obviously there's a very special wind situation, and that's what causes the anomalies in the vibration and not a break in the bearing. So like with the human perception, sensing and perception, the combination of sensing, processing the sensor data, and combining it with background knowledge, with models, with simulations, using AI technologies or other maybe algorithmic technologies, brings us to this point of self and situational awareness. Now, and to give 2 concrete examples where we do this really in products, this is more or less a relatively straightforward example. Nevertheless, I personally find this quite interesting. This is the smart motor. So it's an electrical motor where you put a sensor box on the outside of the motor that can measure some values from the outside of the motor, namely temperature, vibration, magnetic field, and send this to somewhere to be processed, in this case to an edge device that processes the data. And what can you do when you combine this raw measurements with background information? In the motor example, it's the CAD data of the motor, it's a temperature model, it's magnetic field models, is that from these measurements from the outside you can calculate values that you never measured, like the speed of the motor, or using the current plus the magnetic field, you can also calculate the torque, the forces on the motor. By combining this with the temperature simulation model, all of a sudden you can then calculate the temperature on the rotator of the motor, which you never directly measured. Yeah? So you get insights from the raw data by combining it with background information that was never that you would never have gotten without this background knowledge about the motor. So in this example, again, the combination between measurement, background information, and using some AI technology to really calculate the values is the key for this self and situational awareness. Another example fiddles around with those here. Those are these overhead lines, so high voltage overhead lines. They need to be regularly inspected for breaks, for birds' nests on the poles, and for other problems. And how we do this is by using drones. So drones that are equipped with a lot of sensors, like cameras, like infrared sensors, like ultraviolet sensors to detect sparks, like acoustic sensors, and they fly along those overhead lines. And again, in this example, the combination of those measurement values with background information on the context, so on how insulators look like, what are typical problems, geolocation information, plus trained models, for example, for the image analysis, so to detect cracks on the porcelain insulators. This is done via a trained model on the image stream. And this allows you then to more or less autonomously come up with a failure pattern for, or okay and not okay and failure pattern for this overhead line, like there is a bird's nest, or like there is vegetation growing into the path and all that stuff. What we want to do as a next step is, since currently the drones are more or less flying along the overhead line, along the line and trying to make up their, so to say, their mind about the situation. The next step would be that when they detect something unusual, that then the drones autonomously start to inspect this in more detail and decide which kind of pictures they should take, from which angle, which measurement they should use for the situation that they have detected. This is certainly a next step that involves more autonomy as these drones have today, because today they more or less follow the lines. And this brings me to the collaborative IoT part. As mentioned, we think that we will see more autonomy in the things, and then we'll certainly see more collaboration. And why should we do this? Well, in the more hierarchical IoT networks as we have today, it's more or less, even if we have edge computing, it's more or less still a more hierarchical setting where the field devices often more or less communicate only up and down, but to cover more dynamic scenarios where the environment changes, where the capability change, where more or less the communication partners appear and disappear, and the question whether you want to interact with somebody or something is dynamic, then this type of more or less flat structures where, like in a peer-to-peer network, things and humans and clouds and edge app devices can directly interact to perform a task is certainly the more flexible architecture. And this brings me to one example that we do currently. And this is also, by the way, an example that you'd see in one of the challenges, not this concretely, but AGVs. This is automated guided vehicles that perform transport tasks. And in this case, it's different types of vehicles, and they negotiate with the infrastructure who is taking the next transport task. Like in this example here, there is obviously a machine that needs something to be carried to the next machine, and it calls this cloud of collaborating AGVs who can do the job. And the flexibility here in the setting comes with the fact that you can add and remove additional AGVs or take out AGVs, and the system will still work without any reconfiguration and all that stuff. Yeah. So then, since you're now in an interactive workshop, I wanted to somehow link you with two open source activities that I think are quite interesting in this area of collaborative IoT. One is called Mqtt. It's a collaborative IoT middleware that can be used to support such scenarios like the AGV scenario that I've shown. And the second one is a standard that has recently been released by the W3C. As you know, this is the entity responsible for the web, so they created HTML and all that stuff. And this standard is called Web of Things, and it's more or less a semantic interoperability standard. And I maybe today in the lesson about semantic IoT interoperability, you will maybe also hear something about that one here. And there's also an open source implementation for that one. Yeah, I think we will share the slides afterwards anyway, so you find the links in the workshop material. Okay, so this is what I wanted to bring to the table for setting the stage for the lectures that we have today and tomorrow in the area of industrial IoT and AI. So you see related talks here on the agenda, and also two of the related challenges that have to do with edge computing, with AI on the edge, and that have to do with these AGV scenarios. So, thank you.
Okay, very good. Thank you very much, Chris. Yeah, coming from the industry perspective, I want to use some time now on the research perspective, on things that we are working on. So we are doing IoT research since 2008. So we are also for quite some time in the business. And I just want to summarize a little bit like, okay, what are the challenges? Chris already mentioned the key challenge, namely semantics. But first of all, jumping quickly back to what I said at the beginning. So probably you know about virtual reality. So this is again about terms. So virtual reality is that you put yourself into the computer. So you take something like the Oculus Rift, some headset on, and then you're part of the computer. Then the next thing that is there is augmented reality. Augmented reality is you have smart things, or even glasses that augment your reality. That means you still see the reality. It's also used a lot in production already today, that you have glasses on that tell you, for instance, which parts to take from which shelf, or where the error is in the physical hardware that you should fix. And then you have pervasive computing, and the interesting thing is that pervasive computing, you don't need any devices. So it's just happening around you. Why is this interesting? Washington, by the way. Because when you look at this development, so we're coming from the left, going to the right, things are also happening somehow in parallel. The technology awareness diminishes. So when you have a physical space that is enriched with smartness, you're not aware of that. And this brings implications. For instance, regarding privacy, regarding security. If suddenly a robot arm comes and smashes you down, you should be aware of that this can happen, for instance. At the same time, the technology immersiveness increases. So the example with the robot arm, or with if I would walk here and the Twitter wall would follow me, or the phone call follows me, this is very immersive because it's happening everywhere around me and I'm directly part of it. So my physical space is getting changed by the software. The pervasive computing space ideally looks in a way that we do not see that it's technology enriched. Okay. So what are the challenges? So the biggest challenge for implementing IoT use cases in the true sense of doing magic is that you have silos. So you have systems that are not interoperable. So they cannot talk to each other. So you cannot easily program the industrial robots to manufacture a car when your alarm clock at home is ringing, for instance, because there are just no direct interfaces for that. So this is a challenge. It has to do with vendors, with functions. It's also a spatial challenge, so you have to get connectivity. In the LoRa challenge, we'll focus on that, where we have wide area connectivity. It's also a technical challenge, because you will never have the single protocol that is fitting everything. Just think about, you have a Windows sensor that is battery powered, and at the same time you have your laptop, for instance. So both do have totally different requirements on the communication technology, communication protocol, and so on. And therefore heterogeneity is not something that is an error, which we have to overcome, but it's more like, okay, this is a part of the technology. It's because the technology has to fit different purposes there. Something that is done then to bridge these silos is middleware. So middleware, in a nutshell, is taking a distributed heterogeneous system and providing a unified system view. So for you as a programmer, that you can code this and don't have to worry about, so the computer went totally off here. So Apple is not happy about what I'm saying. Okay. I will try to get it restarted. System view on the heterogeneous distributed entities. And so what happened over the past years is currently happening in the home space is that there you have then some hub devices that are connecting different entities. But the drawback is that when you go to the ecosystem of this vendor here, for instance, that they only allow you to do things that they want you to do. So you are not free to create what you want to do there. On the industrial side, it is a little better because there we have standardization. So we have some more standardized protocols like OPC UA, for instance. And so within their domain, these protocols are providing good functionality to do things. But as I told you at the beginning, the cool thing about the AI, the IoT, is that you can connect whatever you want to connect. And yeah, battery was indeed empty, sorry for that. And to do so, you have to integrate the Apple ecosystem with the Google ecosystem, the Siemens ecosystem, maybe with other vendors. And this is challenging, and middleware that that can enable you to do so is not so easy to create. And in the rest of the talk, I want to focus on some important challenges. And yeah, so here we are. Let's just replug. Okay, good. Okay, perfect, good. So, yeah, heterogeneity, distributedness, so all over the world, different devices, brings complexity, and someone has to handle the complexity. So with the smartphone, it's the application developer, because if you have some Bluetooth devices that are connected, for instance, you have to implement the stack that understands the protocols that are running there. The middleware provider could do that, or the one that is providing the device, but the device doesn't know about the other complexity levels. When you want to structure such automation here, you can think about it as shown here. So the pointing device is also not working. Oh, no, I was pressing wrong, sorry. So let me just start also the point thing. Okay, so when you think about this setting here, then, okay, I do it without. What you have is, at the bottom you have the physical environment, so the thing that you want to interact with, and on top of that you have the sensors and actuators, so these are the interfaces to your physical environment. On the other side, on top, you as human want to give some input. So you want to set, for instance, that the robot arm should go to a certain position, or that you want to produce some certain parts of a car at the moment, and therefore you need some human-machine interfaces. This is what we see on top. Then we have software, so this is called services here now, and then we have what Chris already said, namely semantics or data in the middle. So this is the normal compute process. You have input data, you process, and you have output data, and therefore you have this in the middle. And therefore what we do for the past 11 years is we work on semantic middleware, so context-oriented middleware. So context is basically, in the broader sense how I use it, all the information that is needed to fulfill the goal, the tasks that you want to do. So if you want to produce something, all sensor input that you need and all control output that you want to send to the devices that do something. Around that we have then services, and then these services have different purposes. So the ones on the bottom interface these devices that they can remotely manage, and the ones on top provide control and they provide user interfaces. And then you need to connect these services, and what we do is we have a micro middleware with microservices. That means you create small building blocks and you can connect them in order to implement complex functionality. So this is our way to tackle the complexity. And to do so we have different mechanisms. So we have a publish subscribe, and we have normal REST interface where you can get and set information, and something that is used for having direct coupling, so-called virtual nodes. And using such a middleware is very interesting and very nice, because you can use a very simple form of programming, namely you can use event condition action rules to invoke complex tasks. And this is quite nice, and the people working on Challenge 3, you will work a little bit with this middleware and see a little bit what it does. What you see here already is that I put circles, and the circles have the same color. This is of course on purpose, because what you can do is you can unfold the entire thing, and then you have the physical reality, a interaction level layer between the physicality and the cyber, so also in the broader sense cyber physical systems there, and then you have data on top of that. The classical stack looks like this. So you have at the bottom again the reality, then you have the interfaces, then you have software drivers, management software, and then on top you have the humans. And we explicitly put in this context management. This is what our middleware does, and it helps us to provide lots of support functionality, especially also security, where I'll talk about on Wednesday. When you look at it more in detail, the thing, we implemented it as a peer-to-peer system. So you have so-called knowledge agents on all nodes. They are managing the data and also the interaction between services in here. And you have different functionality that has to do with what Chris said before, namely the semantics. So we have something that is called semantic discovery here. Okay, so more details. If you want to know more, you can just approach us, one of us from my team, and Challenge 3 team will also see more of it. So now let's have a quick look at an example. So this is actually the game that we see in the back here, and we have the two sensors on the left and the right, and then we have some alarms, and we have some remote compute functionality here. And the interesting thing when you have a data-driven approach is that the first thing you have to do is that you have to model the data that you want to interact with. So this is the first step when you program. So you don't write the functions, you write a data model first. And so this is what you do here. And then the functionality of the services here is to reflect between the reality and the data, the semantic model of the reality. And this eases the programming of such an environment a lot. Okay, so you have a mapping here, and this one, the task of this microservice here is just to reflect between the virtual representation and the physical entity. Okay. Then we have here our overlay connectivity at the bottom. So this is happening autonomously, so the programmer does not have to take care. And a crucial part of such an architecture is that all these components here are loosely coupled. And that means they all have to work on their own. They do not rely on the others to work. Of course, you can have processing chains where all these here work together to do something, and if a part of it is missing, then the entire process is of course not working. But the components can be used by multiple processes at the same time, which is also an advantage of this abstraction here. And therefore, if something is going down in the chain and someone else still wants to use one of the services, this is still possible. I said it's very easy to program that. So on the right side you see pseudocode for the game here. You see, okay, we wait until the hand is on the boxes, then we set the alarms to on, then we wait for a random delay, then or a trigger, then we trigger the boxes, then we wait until the hand was removed, then we get the times and we set the alarm so that it shows what is happening. And I could not have written it much shorter for explaining you how the algorithm works. And the nice thing is that you can program this almost like that down when you use the VSL, the virtual state layer, so the thing that virtualizes the physical state in this virtual state layer here. And so on the left side, we want to set now the trigger here later, and first of all we want to get the lux value of the box 1. And the nice thing is we can just use a hierarchical notation here, because we just have to find out, okay, where is this address now, where's the instance of this node, and then we can directly go to it and get the data. Okay, this is what we do here. We do the same for the second box, and if both are above this threshold, then we get the time. So this is also very simple of both boxes. Okay. Okay. Sorry, I made it really short. I can show a little bit more on Thursday. And so what is interesting now, I have not this slide here in, but what is interesting, that we have a semantic decoupling. So you can search for, I want to have an input box that is the input controller for the game, somewhere connected to me, and then the system will return you all instance addresses of these nodes. And I will show you a little bit more about the data model in some slides. And the good thing is, if you know now this is the input box in our system, the entire data layout is fixed beforehand. And that means if you know one of the nodes, you can relatively access everything below. And this is quite useful. Okay, good. So now let me click through it again, because I jumped over it, or maybe I can click here. Okay, so Chris mentioned it. Semantics, very important. And so when we talk about semantics, you might have heard about ontologies. So this comes from the philosophy area. So an ontology is about words describing something. And for instance, a real-world example is you would say, okay, a chair has 4 legs. Okay, it's even wrong for these things here, but a chair would have 4 legs, and everybody would understand, okay, this is a chair. Okay. So this is an ontology. So you describe something with a model, so that everybody can talk to each other. So language also uses lots of ontology concepts, because otherwise we could not speak to each other. Then there's something that is called upper ontology, and so this is the common ground for all people. So when you think about, again, language, if you have people who are totally into cars, for instance, they might tell you 1 million parameters of a car. And if you are me, then you have no clue about it. Then you would say like, well, okay, it's red and it has 4 wheels. And so we have a common denominator, some common ground, which is the basics that we need. And this is helpful for interoperability between different people now, but also between different services that want to control something. And the upper ontology is this common ground. When we come now to computer programs, we have virtual objects. So this is this virtual representation of the data. Then we have models that define how, for instance, the game controller layout is of this data, and we have a meta model. And so the meta model is, for instance, XML. This one here is then defining, okay, which nodes does it have, and the virtual object is then the instance. Take home from this slide is just, okay, we have a virtual representation and it follows concepts that we know back from the past, and it's very powerful to do so. Okay, second aspect I want to highlight in this talk is this one here. So once you have this microservice architecture, you need lots of services. And therefore you also need an app management. And my vision is that we have something similar to the smartphones, also for factories and for private spaces, and it's also happening. And the idea is we have developers, they develop something, they put it to one or multiple stores, and from there you can deploy it to the different sites. And there again, to manage the complexity, you need autonomy. So you need autonomous management. So why do you need it? Because when you install a software, or why is it challenging? When you install a software on your smartphone and it doesn't work, well, you have a screen. You can interact with it, you can stop it, you can remove it. But when you have a wall plug, for instance, and the wall plug does not work anymore, you will probably not remove the wall plug and fix your installation there. And it's the same for when you have industrial automation devices. They are normally not accessible in an easy way, and they don't have a human-machine interface. And therefore you have to take a lot of care when you do updates, for instance, have rollback mechanisms and so on. Okay, and so this is what we see here. Could give you more details, but I want to leave it for that right now and come to the end of my part, namely, what can we do with this magic? So I found a very nice application when I finished the slides yesterday, and just want to share it with you. So there are these nice guys, and they created an interesting robot that has an interesting configuration. What is interesting is also the size and power of this device, so this can easily smash you. And they mounted a very interesting thing at the front. Let's see what happens. So this is actually a chainsaw. And so this is chainsawing right now. And so let's see. Okay, so stopped, and so I went forward again, and so now we see what they created. This robot created some 2 chairs and also a table, and yeah, very nice application. And also very nice because we can just do it today. I mean, you will not buy this expensive robot there, but there are also smaller ones, and your creativity doesn't have a limit. So they thought this is a nice application. But why did I put this? Well, because an important aspect that I also want to talk about more on Thursday is this one here, on Wednesday, is this one here, namely security. Part of it also safety. Because if someone, for another reason than fun, or also for the fun reason, mounts a chainsaw that is remotely controllable on such a robot arm and it's standing in front of you, then you definitely do not want that the update cycle is moving it to you, or that someone is hacking into it, or whatever. And therefore, security very important. More about that on Wednesday morning. And this brings me also to the end. Thank you, and Chris and I are open to your questions. So who has a question? Maybe Chris, you also come up. Yeah, wait, we give you the microphone. Maybe one of my people from the back could do that. Here you go.
Hello, everybody. I have a question for Chris, and you spoke about the change between hierarchical IoT and decentralized IoT. And I want you to ask, for you, what is the main driver to go through there? To go to decentralized.
The centralized or now the decentralized?
Decentralized.
The decentralized, right. You know that this discussion about centralized versus decentralized is like a pendulum, and you will see it repeatedly. And so to say, we also had this in the introduction about computing, from mainframes to personal computers, then back to cloud, which is rather a centralized model. Now we are talking about edge. Well, some of the arguments for the edge stuff, so the, again, more decentralized, I've already given in my talk. Oh, sorry. Hello? Yeah. And regarding the decentralized, let's say, collaborative, of course, you could, for example, this AGV scenario that I showed you, you could also have a central controller that knows everything and then manages this fleet. Yeah? But we think that in particular in scenarios where you have a high dynamics in environment, in tasks, changing situations, changing communication partners or partners that need to interact to do something, there this notion of more smart things that can really directly interact seems to us more helpful and seems in this sense a little bit easier to implement and cater for those types of scenarios. But still, I mean, you could also, of course, do this in a central way. Well, that's what we do today, bring the smartness to the edge, to the devices, but of course for many scenarios you could also have a central controller, putting aside the requirements that, or the conditions that I mentioned in my talk, like real time, like reliability and all that stuff, or security, or those, yeah. But currently we think that due to the fact that it is now possible to really have, for example, also AI close to the field because of those nice AI accelerators that you can now really put down to the field devices, to the edges, it is simply, it seems to us, architectural-wise, simply wiser to do it like that.
Hello? Good. So the typical reasons for it are the latency and the resilience, of course, also. Because both you can have, but if you buy it, there's more complexity for the management. Okay, further questions? Here, in front, Stefan.
Hello, my question still relates to that. So you have a centralized system and a completely decentralized system. So wouldn't you say a hierarchical system is like having the best of both worlds? Why would you want a completely decentralized system?
You mean completely decentralized?
Yes.
Well, to be honest, in industries we'll probably never have a really completely decentralized system, simply because of the reason that, for example, for managing the devices, even the simple thing of security updating and all that stuff, updating the apps, updating maybe the models, the AI models on the devices, for that it's in industries, I think you will always have this combination of some central functions like device management functions sitting in the cloud that then can manage the substrate below. But I think what the biggest change is that in the strict hierarchical approach, the feed devices would more or less talk only to the level above. Yeah, but now in the decentralized, they start interacting, so they start talking to each other. Yeah, like the AGVs that now start negotiating who takes the job, without having to go to the central entity. So in practice, in industries, we will have a mix. Yeah, so it will certainly not be a pure decentralized without any let's say, central component.
More questions? Stefan?
Sorry, I don't want to centralize, but the cool thing would be to know which components should be, let's say, in the orchestrator or in the centralized part, and which in the decentralized part. So
yeah, sure.
That was the question. And
okay, and I mean
I think we would know in the in the summer school.
after the summer school, maybe we know more, but certainly functions that you need to manage the overall system, well, lend themselves pretty much to being centralized, at least in those settings that we have in industries. Yeah, but regarding functionality, I mean, I think it's like the border conditions, like mentioned real time and all that stuff, that gives you some hints where it would be applicable, or compute power. I mean, it may be worthwhile to have an AI model executed on the edge, nevertheless learn over fleets in the cloud. So, as I said, probably we'll see a mix of both.
Okay, yeah, then. First of all, thank you again, Chris, for the talk. And just unfreeze. So, as you see here, the next part is you can stand up and have a coffee. So we do the coffee break, and we'll continue at 11. So this means you have now about 16 minutes for the coffee break. So we try to have a little faster coffee break to catch up a little bit with the late start. Okay, see you in about 15 minutes.
ist also ein Mikrofon. Ja, oder? So, hello everyone. So my name is Arne, as already introduced earlier. So I'm very happy to welcome Soumya here today. We know each other already since, I think, 2015 or something. We got to know each other through the W3C, where you are involved in the standardization. And Soumya is a research engineer at Eurecom and doing research and innovation and standardization in the area of IoT, but also smart city and things. And he's very active also at the IEEE, organizing conferences, workshops, and also, I think, editing a journal. And yeah, so we are very happy to have you here. And you will talk a little bit about IoT protocols and middleware. So, thanks.
Thanks, Arne. So he and I, we are friends from quite a long time, so we take turn and praise each other in conferences like this. Okay. So I also had some inputs from him regarding discovery. I'll talk about that later on in this presentation. But before I go into all that, so let me ask you something. How many of you had a weekend party before you came here? Weekend party, like sort of like a bye-bye summer kind of thing. None of you? Come on, many of you are students, I saw in the posters. Really? Okay, I had one on Saturday, really late night. And so yesterday when I was coming here, I was trying to look through my slides. I was literally like this. Where do I start? Yeah, right. And on a serious note, so, this is how I feel when I have to design like any IoT device or any IoT service. Where do I actually start? That's a very crucial point. So later on, when you actually start working on your PhD or later on in the companies, so it's a very important question to ask. Like, should I start with security or ease of use or whatever it is? Now, if you look a little bit closely towards this picture, so there's a lot of things written at the bottom. Can you identify a couple of things that's missing from here? Yeah? Sorry? Security is written. Which first? So anything? Can you see what is missing from here? Resilience, yes. It kind of ties up with security. Context domain, yes. Anything else? A very basic one that every one of us, we generally tend to miss. The answer is communication. So when you start developing software at a very high level, so you sort of think like the communication and the protocols for communication, it's sort of given. So nowadays we really don't care about the internet or the web parts. We sort of assume that it's there, and what we need, we can actually query the web or send a packet through the internet and we can get the response. But when it comes to Internet of Things, it's a little bit tricky than that. So in my presentation, I'll go through two communication protocols. Constraint Application Protocol Co-op and Mqtt. These two are pretty standard these days. I intentionally left the HTTP part behind because you are using it since a long time and it's pretty well known, so I'm not going to repeat the other stuff. And then Marc-Oliver already mentioned a lot about the middleware, so I'll show you some very basic middleware that you'd need to work on any IoT project, especially on the challenges, and show you some demonstrations how those things work in real life. But before going into that, so just some very high level and very generic aspects for you to understand. So these two things always remember. Some very generic vision for the Internet of Things. So there are two. So it's something I took from his slides as well. Things interacting with external services. So we all know about the clouds, edge computing platforms. So in your home, if you have, let's say, a Fitbit, or if you're wearing one right now, so it's sending data to your phone and then probably sending it to a cloud. So you have the Fitbit interacting with a cloud, and we can also have things interacting with other things. Like in your home, you can take a tablet, interact with your smart fridge, context like that. And the second part is these connected things, they can also react autonomously to the environment. For example, Imagine this building. So in the evening, when all of us will leave from here, maybe there is a presence detector that can automatically turn on the lights, turn off the lights and the other outlets because all of us has left. So it's another example on how things can interact autonomously to the environments. Now the next 3 slides I have, it's what I call the good, bad, and ugly of Internet of Things. I really like this one. Any of you play tennis? You've 1, really good. 2, so probably, okay, some more. So you have used the traditional rackets on the left, right? All of you? Have any of you seen the one on the right? Sorry? So you have used the one on the left, for sure, no? Really? Maybe, yeah, another one, okay. But something similar, okay? Not exactly that one in the picture, but something similar. But have any of you has seen the one in the right? So one company, probably it's a French one, so they managed to connect some sensors into that, and that sensor actually generates a lot of data about how you are training. Analyzing those data could actually tell you where you are lagging in your training. So it can actually so your coaches can actually give you some data-driven results. Maybe your grip is not correct or the way you are hitting the ball is not correct. So those things could be justified from the actual data. So this is one of the very, very good things of Internet of Things. Now the second one, the bad part. Since artificial intelligence and IoT both are the connected themes of this summer school, so I took this one up. The story behind this is last year, I fell sick quite a lot of time. And my doctors, and when you have two of your brothers who are doctors in the family, so they are awfully, caring and asking how many times you are sleeping while you are recovering from certain illnesses. So I was like, okay, you see my data. So they're like, that's not good enough. You have to sleep at least 8 hours every day. So to track that, I bought a Fitbit and I started monitoring my sleep. And this is 1 week of real data coming from my Fitbit. So you see from April 8 to 14, you see 7 hours, close to 7 hours, 8 hours, it's fine. But there is a huge anomaly on 13. So what happened on 13 is I was like really, really tired. So I slept on my couch with my Fitbit on and I was binging on Netflix. And that started around 7:30. And I did not binge for I don't know, 12 hours, but I slept somewhere around 11 or midnight. But Fitbit actually collected the accelerometer data, passed it through their machine learning systems, and they are saying I slept for 12 hours and 45 minutes. But, so this is not correct. Somehow this messes up my weekly average. But they have already data about the rest of the days. And if you see, April 13 is a considerable amount of anomaly with the rest of the data. So this could have been a point where the device or the service asked me, did you actually sleep for almost 13 hours that day? That didn't. So artificial intelligence, machine learning, deploying them in a very, very open systems, this is not correct all the time. So you have to find a way to bring the human into the loop if you start to spot some deviation from the pattern. In this case, it's quite a lot. This is one of the part. And the really ugly part is what I call the dark side, is about the cybersecurity, privacy, and all those things. So recently, I read a report that it published in one of the top security conferences as well. So somebody asked many, many companies around Europe about how much data you have collected for me, give me all those data back. In many cases, these companies, they didn't check or validate from whom the request was coming, and they were giving out all the data. So now imagine I'm a bad guy, and I managed to hack into his email address because he trusts me, and I send out emails to everybody saying, okay, give me Arne's data. And I start to do something malicious around that. So this type of things can happen. Privacy continues to be an illusion. Cybersecurity, in many of the cases, people are writing in their websites that, okay, we have military-grade cybersecurity. So everywhere you see military-grade, so you can be, for sure know that they are writing storing all the passwords in plain text, not even in the hash in their backend. So this is not good. So, and from time to time, I'm doing a cybersecurity analysis of the IoT works that I keep on doing. And when I review the security logs, I see almost like a weekly distributed denial of service attack against our IoT platform. Also very, very increased amount of attacks in terms of scams, many other things like extortions, ransomware, like you have to pay this much, like 0.345 bitcoins for me, or otherwise I have encrypted all your data. This kind of things are coming. And a company actually got hit by it. So I was in a conference in Liverpool, and when I saw this tweet, so Norsk Hydro, it's a company, they got actually hit by a ransomware who demanded a lot of money out of them. So these are some very basic things that you should keep in your mind, for example, for your later on, if you do your PhD or go on work on the companies. So in my rest of my talks, so I'll come back to the original aspect of my presentation. I'll focus on two key aspects. On the communication, so that's where we have the protocols, two communication protocols, and the softwareization that's basically eating every aspect of our lives. Now, jumping straight to co-op. Now, before I go into the different parts of co-ops, what's very important to understand at this point is what led to development of a new communication protocol. And I'm talking about the era from Marc-Oliver's, very nice timeline. So between 2000 and 2008, at that time, we did not have iPhone, we did not have Android phones, or any such fancy gadgets that we have in our pockets nowadays. So what we had at that time is very, very constrained devices like that. 8-bit, 16-bit, sometimes 32-bit microcontroller. And people were having business cases. So a lot of embedded developers it was something I was aspiring to be when I was in undergrad school. So we are having business cases which required these type of devices to be connected to the internet through constrained networks. Constrained means very low power, sometimes even lossy network. We had to support multicast and with very, very low protocol over it. So these were some of the requirements. And what we had at our disposal was at HTTP. And HTTP was not simply fitting the bill, because HTTP was created to be run on devices like this, not on devices like microcontrollers. So people actually considered design requirements like this. So if you see on the right-hand side, so let's see. Okay, this doesn't work. So if you see on the requirements, so we had to satisfy a lot of them to create something like this. So the protocol, it's basically runs on top of IP, UDP, and there's inbuilt security mechanism in terms of DTLS, and then you have the protocol co-op on top of that. So at this stage, it is existing as an open IETF standard. So any of you can actually go into the IETF website, take the specs, read through it. The second point is very, very important. It has a compact 4-byte header. So you can see 4-byte is very, very compact, and it's been able to support it by different types of microcontrollers that we have even running today. And if you are utilizing co-op in one of the challenges, so you could note the UDP port that you would be using, 5683. There is also other features like asynchronous subscription, built-in discovery, many of them. And very quickly, I want to show you the message header. So this is how it looks like. It's taken directly from the specs. So you have one field for version, then what type of message you are sending, the token length, the code, message ID, and the token itself. And that's pretty much it. And then you pretty much write the payload. For example, if I want to see back in my home, what is the status of the door, or if it is locked or unlocked, so I can pretty much send, give me the status of the door in the payload. So 4 very, very important features for co-op. So it's a very, very efficient protocol for RESTful communication, ideal for constant devices, I already told you. And it's very, very specialized for machine-to-machine applications. Co-op was created to support this type of machine-to-machine or thing-to-thing interaction. And it's very easy for this protocol to be operated with HTTP. So for that, if I go back to this slide, so imagine on the right-hand side, you have the constraint network. These devices need to be exposed to the internet to do something, but you cannot directly expose them to the internet because they are constrained. So these devices are basically hiding behind a proxy or a gateway. So here, when you are sending a co-op packet to the proxy, that is basically doing the translation between co-op and HTTP. So it could be done through one of these methods in the middle, get, post, put, delete. So these are some of the things that's readily supported in HTTP. So it was basically inspired from that. And also there are other features, for example, in the web. So we are writing HTTPS, then www.google.com. So you can write the similar thing, co-op, then your URI. There's asynchronous transfer model, URI support, all that. For example, this is how the co-op URI would look like on the top. And like we have HTTP and HTTPS, we also have co-op and secure co-op, so co-op S. So pretty much you can utilize the built-in DTLS for the security purpose. This is how a co-op request looks like. It's a simple client-server architecture. So you can set a connection saying, give me the status of the light, and in the response, you'd get the content in there. And since we have to support reliability as one of the, by design into this, so it's very, very important to take into account the timeout or the packet loss. It comes because co-op is built on top of UDP. It's not one of the most reliable protocols out there. So when a client sends a packet and it doesn't get a response within a certain timeout, it would resend. So maybe because the packet was lost while going or coming back. So you have the packet loss situation. Another key aspect of co-op is observation. In Internet of Things, when you write certain web services at the very high level, it would depend on the real-time data that you would procure from different sensors. So for example, let's say we want to monitor the presence detector here, and we don't want to query the presence detector every 10 seconds, but we want it to trigger us when there is nobody in this room. So what we would do is send an observation packet to that particular resource. And that's pretty much analogous to registration. And when the situation for that sensor changes, it would send notification saying, okay, now I do not see anybody in this room. And then based on that real-time information, you can turn off all the lights in one go. So this is another key aspect. If you want to experience some of these things hands-on, so these are some of the well-known open source projects that you can utilize, and you can follow pretty much the tutorial down there. So you can set up your own co-op client, server, start playing with it, and have your first Hello World or Hello IoT program running. Another information I'd like to share is that it's not only a research project, so it has started to get some commercial tractions in the actual IoT market. So ARM, they have their own operating system called Mbed, which supports co-op, as well as there are some other actual product out in the market. And I included some references for you as well. So if you want to have some sort of background reading or other pointers to go through, you can do it from there. And now I will jump quickly onto the MQTT part. So what was predominant in co-op and HTTP is like it's pretty much a client-server architecture. So you have a co-op client and you have a co-op server. You have a HTTP client and you have a HTTP server. Now in MQTT, it's sort of where you have like a paradigm shift. So we are moving away in some sense from the client server into a publish subscribe paradigm. Here, all the configurations are broker based. So we have one broker and connected clients. So the broker receives subscriptions from clients on different topics. The topic is a very key aspect in MQTT. And then the broker receives the messages based on these topics and forwards them to the subscribers. Some of the use cases that MQTT is supporting is that it's actually a push-based paradigm instead of the pull. It's quite reliable when there is unreliable network. The reason behind this, MQTT is built on top of TCP, so it inherits all the nice and beautiful features of TCP. It supports constant devices, low bandwidth, high latency, all that. Now, this is one picture to show you how this thing works. So let's say at the center we have one broker. So imagine this as like a cloud server where each of the publishers, like the different sensors, they are sending data to particular topics. So in this room, if there is a presence detector, it can say, it can create a topic and it can send data to that. And we have a lot of other collected clients who are subscribers, so who are subscribing to that topic. So the way it works is that when the sensors generate data and send it to the topic, it is automatically forwarded to those subscribers. The last picture, I mean, the arrow has to be reversed. So you see 2 publishers, the data going into 3 subscribers at the same time. So this is how, on a very high level, the paradigm is working. And on the implementation sides, high-level application or web developers like me, we are very fond of it because the first thing is the client is very, very easy to develop. There are many open source things, and if you want to do something from scratch, you can do it. It's very suitable to connect, constrained devices because the least, the smallest packet that you can send is like 2 bytes. It's pretty much nothing. And it's connection oriented because it's built on top of TCP. And there are several features that you have to understand if you want to really use them. For example, quality of service, written message, wildcard, last will and testament, persistent sessions, and heartbeats. So I'll try to cover some of them in this presentation. A very important aspect is the quality of service levels. So in my work, I have used HiveMQ and Mqtt as brokers. So I took the example from HiveMQ to inform you about the 3 QoS levels. So imagine we have one sensor on the left. It is sending data to the broker, which is HiveMQ. So if you set the quality of service at 0, so it means like a fire and forget. So the data is generated, it's sent to the broker, at most 1 delivery, and the message is not retained on the client. So this is how the QoS 0 works. It's not one of the most reliable thing, but if you are in a really constrained environment, so that's the one you can go for. The second one, QoS 1, so here the sensor, let's say the publisher, when it is sending data, it can set the QoS as 1, so it means at least 1 delivery. So you are assured that that packet would go to your broker, and the broker will send an acknowledgement. So until you receive that acknowledgement, you retain the message. Maybe there is a timeout. If you don't receive the acknowledgement, so you can resend the message. So that's the QoS 1. And QoS 2, so that's exactly 1 delivery. So this is the most safest and the most slowest process. Because in TCP, we have 3-way handshake. This one has 4-way handshake. So you'd send, you'd get a reply, and there are 2 more to do a lot of black magic inside. So in most of the cases, I am utilizing QoS 1 because we have enough powerful devices with Raspberry Pis in your phones and all that. One very, very quick slide on HiveMQ. So I particularly like it because many aspects, like it has very high performance MQTT broker, so you can literally bombard it with a lot of messages, a lot of subscriptions, still works. It's built with security in mind. It's very important in some of the use cases we have. It's open source, and you have the Java plugin for the system. Very, very useful for me because I'm always writing software in MinStack. Supports bridging, clustering, so you can actually develop applications determined for the enterprise use. For example, when Chris was talking about really high-level AGVs and other aspects, so if you really want to go into that level, so you need to support clustering. Very quick slide on 2 more things, the written messages. So here, the broker saves the last message for a topic. So if you want to enable this, so the last known value is retained. Okay, so if someone from the subscriber wants to get it, so you can get it through the written message. Last will and testament, it's sort of, somebody took it literally, and here the publisher can define this and send a message to the client, and in between, if the client dies, that means if it goes like offline, so even if a subscription comes after that, so you'd be able to retrieve from there. So this is pretty much very, very high level concept of the last will and testament. Now going into the data transport, Mqtt is pretty much payload agnostic, so you can send data in any format. So not only just binary data, so you can send XML and any other things. There is no defined metadata or data types. But I always suggest your clients, connected clients like publisher and subscribers, they must agree on certain serialization, whether it's JSON or JSON LD, it's up to you to define, but doing the serialization would help you on the higher layer on how to interpret the data as well as how to make meaning out of it. Now, the communication pattern. So this is the interesting part of Mqtt. And remember, I mentioned that it's actually topic-based. So topic is a very, very key part here. Consider this building. So I would show you how this hierarchy works. So we have several such buildings. So if we call this building 1, then we are already on like first floor, I think. So there could be different floors. Different floor has different rooms. And in each room, there are different sensors. So if you want to indeed talk to one particular sensor, so you can build the hierarchy like this. Building 1, then floor 1, then room 1, then temperature. And there are 2 types of wildcards here. So one for single level, which is the plus, and one for multiple level, which is the hash. So the single level works like this. Imagine in your home, so you have temperature sensor in the living room, in the kitchen, you have a lamp with brightness sensor in the kitchen, and you can pretty much create a topic like this. So on the high level, your hierarchy is my home, then ground floor, then you put a plus. So this plus can correspond to anything that is between the ground floor and the temperature. So that's why the first 2 topics are valid, but the last 3 topics are not valid. For example, if I take the third one, ground floor, kitchen, brightness. The brightness doesn't match with temperature, so that's why it's not valid. You got how the single level works. Now the next one is the multi-level. And since it's multi-level, it always comes at the end. So this is one of the distinctions. So the single level can come in between, but multi-level will always come at the end. With this, you can actually subscribe to many, many topics. You pretty much can, if you want to avoid subscribing to 100 topics, so you can pretty much use this one. So for example, if I use the same example, so let's say this particular multi-level topic would allow you to subscribe to first 3 topics, not the last one, because it's not after ground floor, it's after kitchen. Some of the best practices, so here I summed up pretty much my personal experience and some of the best practice from the literature. So if you are interested, follow this later on. And since my background is security, I always somehow find a way to bring security into the picture. Like co-op and HTTP, you also have Mqtt and Mqtt-S. S is for the secure part. So you can utilize the same SSL and TLS certificate for HTTP to do the Mqtt-S aspects as well. Now, so with that, the first part of the communication is over. So now I'm more excited to go into the middleware, because that's where all the magic is, and that's where I work on. So Marc-Oliver talked a lot about the middleware aspects. And I can sum it up why we need middleware in one sentence. It's just to handle the complexity that's present in so many levels. So you have the massive scale, because just among all of us, so let's say we are 25 to 30 people, so we probably have like 100 machines with us, with watches, phones, laptop computers, and so many other connected devices. Now, if you imagine that on a city level, that already goes into probably tens of thousands. And in a smart city project, so if you want to make use of crowdsourcing to get certain information, so you have to take care of this massive scale, continuous and vast amount of data that's coming like almost every second into your edge computing or cloud computing system. So what are you going to do? Have some sort of data filtering so that we are crunching only the interesting part out of the data that we are getting. Then the complex system. So I'll talk about that in the second slide. And also we have the question of open access. So Marc-Oliver talked about that as well. So a lot of vendors, they don't want you to do a lot of stuff because they are trying to limit the access to their systems. And on the other hand, you have vendors, They're pretty much open, let you do a lot of things, so as to decoupling, the data producers, consumers, and everything that goes on in between. So now talking about this middleware from my personal experience in Eurecom. So we started doing this probably in 2012, 13. And the first use case that I had was creating a smart gateway for homes. So it was like a monolithic version, very simple. So we had certain IoT devices that we have to connect to a gateway, and we have the phone. So individually, you can see how many devices are connected. If they are on or off, if you see that nobody in the room, you can turn off the light, this kind of aspect. But pretty soon, what we discovered is that since it was monolithic, if I want to change something in the data exchange, that was affecting the way I do local storage. If I want to do something in the discovery, that was having some sort of effect on actuation. So this codependency was not correct, because maybe if I want to release a software right away for the industrial partner, I have to be careful because it is touching different other places as well. And at the same time, if I do anything on the 3 web services on the right, the local storage was also getting affected as well. So we started to think how we can decouple all these things from one another. And the obvious answer was microservices. Go to microservices. So we pretty much went there. And at the same time, our research agendas got extended, and we started to include different aspects of edge computing. So I talked about this massive scale and the filtering part at the beginning. So that is what we wanted to bring, and we wanted to bring it at the level of the network, edge of the network, not in the cloud. So we pretty much started to do it with IoT data validation, metadata annotation, local processing, all these things done in an edge server, and then in the cloud, we pretty much have other services like data exchange, registration, discovery, the storage for long term, all these things. And over the years, it got like really complex, because we now have use cases with real cars. So we have managed to connect a BMW car with our IoT platform, sending data the upstream so we can visualize them, even turn on, turn off certain aspects like the windows and other things from our mobile phones. So you can see it became like enormously complex. And to arrive at this level took us like 5 years. So if you have to do something similar in your PhD or later on in your work, so can you afford to invest 5 years? She is already saying the correct answer, no. So this is where middleware comes into the picture. So nowadays, a lot of European projects, they are providing a lot of open source middlewares. So you can readily take something from there, see if it does your bidding, and you can plug it there, because everything is microservice nowadays. But if you have to add or remove certain features from this, so I mean, the benefits of middleware again would come into the picture. Before I go and talk about 3 middlewares in my presentations, I'll quickly talk about the microservices. So this type, on the right-hand side, so you see that we have created like a very loosely coupled web services. And the most benefit that I can see from my experience is that I can readily inject something without disturbing anything. That's the main benefit. Or I can update something without disturbing anything. And another very key aspect is that since all of them are loosely connected, so each of them are having a unique way of communicating with each other. As long as you respect that, you can pretty much do anything inside the microservice. So I am very much writing the software in Node.js, MongoDB, so mean stack. My current boss, he's hating that aspect totally, and he's doing it in C++. So this type of architecture allows us to love each other and pretty much be independent of our programming nightmares. So whatever he's doing in C++, if he manages to send me the message I want, I'm happy. I don't have to do anything. But if I go back to monolithic, either he has to compromise, learn Node.js, or I have to go back in C++, which I really don't like. So these type of things are very, very important. So these are one of the design questions behind the selection of different middlewares. how are you going to program it, different kinds of databases, what type of architectures, design patterns you are going to take into the picture. So these benefits I already said, so I'll skip. I'll come into three basic aspects of the middleware. Now, the first one is uniform data exchange with connected devices. Now, if you have seen, if you have been into any online IoT marketplaces, so you'd see everybody have their own set of sensors. Samsung has its own, then LG has its own, Google has its own Google Home nowadays with many different sensors, all that. So there are probably like 1,000 different types of sensors, 1,000 different ways of accessing data, and probably even more ways of controlling something. Who among you would like to write a web service for each of them? Write a web service so that it individually connects to, it has its own way or like a silo-based way to connect to each of the sensors or actuators. Yes. Yes, perfect. But would you literally like to add, go into that silo or have something like a standard so that every sensor can talk through that? Yeah, so that is what we try to do here. So heterogeneity at the very bottom is a big nightmare for people sitting at the top of the hierarchy like me. So if each sensor has its own way of sending data, then when I have to combine different sensors in my intelligence, that becomes a nightmare. Because I have to understand how each sensor is talking. Okay, so if you travel to Serbia, something like you know English or you know Serbian, you're fine. But I don't know Serbian, so when I'm picking up something from the supermarket, I have really trouble to understand what is going on. So same thing would happen with this type of use cases as well. So if you don't know how to make a layer where uniform data exchange will take place. So that's why what we do is that in our research, we utilize sensor measurement list. So this is one of the standards coming from IETF. So it shows you a uniform way to exchange sensor metadata. I put the metadata in the quote because the measurement itself does not tell you anything. For example, if I tell you, let's say 100, what would you understand? Let's say my sensor tells me 100. Sorry? Yeah, the first question is, what is the unit? Let's say I tell you it's Fahrenheit. Then the question is, how fresh is the data? What time? Then, what else do we need to know? Sorry? Source, yes, let's say the source, yeah. What else? Localization, it's important, but not always. But it is important to know. One very, very important aspect to know here is from which, what is the domain of operation of the sensor? Or what is, from the unit you can understand what is the sensor, but the domain is very important as well. For example, this one has accelerometer. And in my project, I wrote two applications. So one is to detect if there is an earthquake, and another one to detect if there is any potholes in the road. So same data being fed into two applications, and two of them are interpreting in different ways to tell you something. So that's why the domain of operation is also important. So we have to punch all these information, not only the measurement, but the name, ID, unit, timestamp, all these things, creating something what we call data about the data. So that is what metadata is. So this metadata helps you in semantics and many other things that Dan and Arne is going to talk later on. Now, if you look into the first points, it's called sensor measurement lists. What about actuators? We have to control certain things. For example, when we all leave, somebody has to turn off the lights. So the turning off is the actuation part. So should we come up with certain another standard for the actuators? In our experience was that was like a very, very cumbersome process. So we extended the scope of SenML to include actuators as well. So by doing this, we avoided a lot of things while we kept the same model so we can interact with both sensors and actuators. So the advantage is that, so now we have middleware providing you with uniform mechanism to interact with both sensors and actuators. And believe me, any vendor who is complying with this, you can directly, plug it in your IoT system. Then automatic device management. So somebody asked a question about distribution and centralization, and device management is a very important aspect keeping in the distributed environment. So middlewares normally provide you web services to do automatic device management. So it basically allows you to read, write, and update configurations. For example, imagine I have this phone, and when I'm home, it is connected to my home network in Wi-Fi. So when I'm hotel, it's in the hotel. When I'm here, I'm connected to the local network. So somewhere there's an intelligent agent that is doing the configuration of the Wi-Fi automatically. So this is something you have to do with your devices as well. Imagine, so today, so you are doing, let's say, master degree or PhD, so you have a smart home. You have like 30 devices that's helping you to do a lot of things. Tomorrow you move to another country. So you have to take all these devices with you. Do you want to spend 3 days configuring them in your new home? Or even, I'm procrastinating buying a new computer because I have to configure so many things. So I'm using it for like 6 years now. You see the level to which it goes. So if you have to do it manually, nobody's going to use it. So all this technology would be off the shelf, but nobody will buy. So we have to find a way to automatically do this read, write, and update configurations. So based on your Wi-Fi or certain other information that you can say through Google Home or Amazon Alexa, it should do it automatically. So this is one of the key requirements of the middleware as well. Another thing is enabling device discovery. So I'll talk about it a little later on. Receive notifications, very important. Let's say you invite your friends. So after the party on Saturday, so I went to one of my friends because she stays quite close to the airport, and my wife was like, okay, we can stay there, then you can go to the airport from there, and like, okay, let's do it. So when you have house guests or people coming in, so you have to give them access to your devices as well. For example, the room they're gonna sleep in, maybe turn on the light, certain things. So you have to know before whether the device in that room is working or not, okay? Maybe in future you don't have a physical switch through which you have to turn on and turn off the light. It is always through your phone. And if that is not working, so then you're pretty much in a very tough spot. So if a device goes offline in your home, you have to know. Or if let's say you are in the office and you don't expect anybody to be in your home at that point, and somebody opens the door, you should get a notification because it's an outlier, it's an anomaly. So receiving notifications is very important, then having proper access control. So my friends can give me access for 2 days, and when I'm gone, that access should be automatically revoked so that I cannot remotely open the door in her apartment from here. So these are some of the things that automatic device management already does. And to do that, there are many open source frameworks, so lightweight M2M, many things. Pretty much they do 4 things, let's say. So the first one is bootstrap. So bootstrapping means you are provisioning certain informations. So how many of you bought a phone recently? Android, iPhone, anything? One? Anybody else? No? You remember when you first bought your phone, right? So you pretty much open it, you turn it on, then you have to put a lot of things, like for Android, your name, your Gmail, then the Wi-Fi password, all those things, okay? Same thing happens with these IoT devices as well. So these days, IoT devices, many of them I've seen, they come with like a default password like 1234. So you have got to change it to a complex one, for example, 4321, right? So those are the things you have to do at the beginning. Then client registration. So another important part. So as the high-level framework knows, who are we snooping onto? Whether it's Arne, or whether it's me, or whether it's you. Then service enablement. So all the things I talked about, and then information reporting. So these are the 4 high-level steps that's part of any automatic device management. The next one, so this is where things start to get even more interesting. IoT platforms, they are pretty much dependent on sensor data, right? If you develop your application and where you need data coming in real time, and you don't know whether that device exists into the real world or not, so what you have to do? You have to pass through some sort of discovery. In other words, you have to pass through some sort of search engine for the Internet of Things. For humans, we know what to do. So you can even talk to these search engines nowadays. But what should an IoT platform or IoT web service do? Any ideas? Yeah, discovery, but how to discover? Publish, subscribe, think one step before. Sorry? Very good. You? What? Call to a discovery service. How would that work? That is the main thing. So as you mentioned, so one client, it can announce itself. For example, Wi-Fi, it announces itself. So on your so when I connected to the local networks, I pretty much looked up, where was it? Wake 1 event, yeah, exactly that one. I found it, I pressed, I put the password, and that was it. But it required some sort of human intervention. It was not automatic. So the middleware also faces a lot of challenges like this. So we have a client, so it can, so one thing, it can announce itself using Bluetooth, okay? Or somebody can announce itself in a network. So there are protocols to do that. Or somebody even can register themselves in a directory. Okay, I'm present in this directory, so if you send a query here, so you'd find me. And this is a very, very nice picture, but in real world, looks like this. Too many of it. Even for a tiny problem, like to discover a thing, you have so many options available. So you see how enormously complex things are, and engineers like me, we are trying to not only solve the complexity, and we are increasing the complexity as well. So in other words, so discovery scenarios, so there are like many of them. So you can search around me as in your physical or smart space. So it could be through URI beacon, NFC. So in the network, you have protocols. You can search in a directory. You can search across peers. You can search for metadata. You can do semantic-based search. So Dan will talk a little bit about Sparkle and other things. And if you want to really create a search engine, so these are like baby steps to go there. So you need a configuration registry, so where everybody would, from everywhere you would pull configurations. Then you need to index them. Then you have the actual search engine which would actually provide the lookup facility. Then you also have the question of lifetime. So for example, maybe I want my device to be available for a certain amount of time, not after that. So resource sharing or privacy concerns, a lot of things would come into picture. So I intentionally wanted to talk about these 3 high-level things and then show you some demonstrations on how these things actually work in real life. So we had a project in which we had to connect an actual car, send its data to a external service, and then we have an Android app which would pretty much see what is going on in the car and then remotely play around on it. So we spent like 4 months and created an 8 minutes video of it. So this is the setup that looks like. So everything I have talked to so far is, you'll find it somewhere. For example, we are having data generation using SenML. We are pushing it to the roadside unit. There's a gateway. The Android app is seeing the same measurements. The app is also doing discovery. And before that, the registration and automatic management is taken care in the IoT gateway. We also put in place a simple amount of security into it because we knew it's a controlled environment. Nobody from outside would be able to access it. So let's see. I'm hoping this would work. Okay. So the project was called Datta Tweet. It's pretty much like we are all sending out tweets with a particular hashtag. The idea was that the car would be able to tweet what is happening in the car, and there would be an Android application who is making something sense out of it. So this is the first step. So this is where we are accessing some parts of the onboard unit that goes in the car, and this is the antenna through which the data transmission would take place. So the SendML, so the uniform way to getting data and all that. So it is here where we put it into the onboard unit. So this is one part of the setup. This is where you'd see that measurements are sent via the OBU. So we were pretty much sending three aspects. The transmission power, CPU load, and something else. This is the roadside unit setup. So here, okay, it's better I go to YouTube. Sure. Seems I cannot control it. Every time I try to show a demonstration, it has some sort of demo effects. In real time, it doesn't work. It worked perfectly that time, but not in front of audience. It's too shy, it seems. But the main idea was that here, so this is again, you have to be patient a little bit on this side so I can explain the other part. Okay, I'm able to pause. So the idea here is this high mast is hosting one antenna, what we call a roadside unit. So on top of that is the antenna. So this is what will receive the data coming from the vehicle. And it would transmit the data into the workstation that I set up. So this is the edge computing part. So all questions about gathering the sensor data, sending it to the mobile application, doing some local analytics, everything is housed in here. So this is the roadside unit, the computational box itself. And the Raspberry Pi was the actual gateway which was doing it. So it's pretty much powerful. And there you see the car in the real setting. So it's in a remote position. So we took this particular position because we had a line of sight, just wanted to be sure that there is no loss of data in between. And that's me about centimeters away, setting things up. Now we are launching the gateway operation. So our web service runs here, waiting for measurements. So all these measurements coming from the sensor will come using SendML. And this was the initial storage. So I had another screen to go inside the database to show that initially there was nothing. And then when we start to get something, there would be something. So I asked my friend, okay, start sending stuff. So he pressed the button, and then we were waiting. There it comes. So you see the post request coming with different aspects, like the configuration of device endpoints. So I talked about we have to store certain configurations with the system. So that's what it was doing before. Then it started to send the sensor measurements. And then we asked the car to move, and we could not find the car anymore. You can see all that in the presentation. I'll give everybody the slides. I'll go into another presentation. So this one is a little bit complicated. Why is it the same thing? So this one is about high precision positioning. This was another project that we finished last year, and here the idea was to utilize Internet of Things to provide even precision position that goes beyond the precision of GNSS. So we wanted to bring it to really 5 to 20 centimeter level in that case. So we saw that Internet of Things itself not enough. I mean, the intelligence is not enough. We have to have connections to real hardware that's deployed in the roadside in different areas, and we have to collect data in real time, map them, so we are able to tell in real time in autonomous cars where they are moving. So let's see. I'll turn off the sound. This project was called European-wide Positioning Service Platform, providing 3 main aspects: context switching, positioning, and demonstration. And we had some ideas about how to create a marketplace out of it in the future. The first thing here was to determine what is the best positioning algorithm. So we do it with an Android app. So 3 cars. Arne is telling me we are running out of time. So probably I can give you the slides. The video is on YouTube, so you can take a look. I will give a quick conclusion. Yep. So 3 main points. Digitalization, softwareization, they are pretty much taking over different parts of our lives through Internet of Things, middleware, communication, all of that. And software engineering becomes a very, very central part into all this. Whether you want to do communication, whether you want to do middleware development, semantics, whatever you want. Although I didn't go into, okay, I took it from a healthcare presentation, that's why it says healthcare, but it pretty much applies to every other sense. Although I didn't go into the security, privacy, trust, because it would be covered separately in this presentation, but even if you are writing 20 lines of code, think about these 3. Okay, always think about security, privacy, and trust. And when you are doing software for a long time and you have multi-party computing going on, things like on the right side happens more than you know. So it's just something you have to deal with it. So with that, I would say thank you. And as Lufthansa says in the in-flight, best way to learn German is Prost. So I'm hoping we'll do it in the evening with everyone. Okay? Thank you very much. Yeah. Who wants to ask this question? Yes. Yes.
Hello. Do you have any comparison power performance between Co-op and Mqtt?
I had a student who did it. I don't have the results with me right now, but I can dig it up and send you.
Thank you.
Yep.
Okay. Question? Very good. Did we thank him? If not, let's thank him once again. And now you're probably all hungry. We'll go now to the place that Katerina knows. So please quickly get your stuff. You can leave everything here. We also leave our equipment here, which is probably more expensive than yours. So they will first take ours. So just go to the exit and we'll walk